In this class, we have looked at polarities of bonds. One way to rank the bonds in order of increasing or decreasing polarity is to calculate the electronegativity differences of each of the atoms in the bond. This electronegativity difference gives us the relative polarities of the bonds. Instead of finding relative polarities with electronegativity differences, we can find absolute polarities using a calculation for dipole moment. Dipole moment, represented by the Greek letter mu, is calculated with the equation mu equals q times r. Q is the absolute value of the charge on each of the atoms. Each atom in the bond will have the same magnitude but opposite signs for their charge. For example, in the benzene molecule, carbon has a partial charge of negative 0.0622, and hydrogen has a partial charge of 0.0622 electron units. Essentially, 6.22% of an electron is transferred from hydrogen to carbon. The distance between the charges is represented with r, and the product of Q and r gives the dipole moment. We will go through some examples of calculating the dipole moment in the next chapter. The dipole moment is a vector which has magnitude and direction. We can represent this vector with an arrow that has the tip pointing towards the more electronegative atom, closer to the upper right of the periodic table, and the plus sign on the less electronegative atom. For example, in the CH bond, the arrow is pointing toward carbon, and the plus sign is on the hydrogen. In the BF bond, the tip of the arrow is pointing toward the fluorine, and the plus sign is on the boron. We can take the vectors for each bond and add them together to find the overall dipole of a molecule. Since it is vector addition, both magnitude and direction are important. One example is in the CO2 molecule. The partial positive end of each bond is on the carbon in the center. The partial negative end of each bond is on the oxygens on the outsides of the molecule. Both bonds are CO bonds, so they have the same electronegativity differences and the same dipole moments as each other. Therefore, their magnitudes are the same. However, they are pointing in opposite directions in three-dimensional space, so they end up canceling out. Something like plus y minus y equals 0. The CO2 molecule has polar bonds, but is a nonpolar molecule. In the water molecule, the OH bonds also have the same magnitude as each other. But because there are lone pairs in water pushing the atoms into a bent molecular geometry, the OH bonds are not directly across from each other. The Lewis structure may make it seem like water would be linear, since it is drawn in a straight line. But in actuality, the bonds are not in a straight line with each other, and so the vectors are additive rather than canceling out. There is an overall dipole pointing away from the hydrogens and towards the oxygen, so the molecule overall is polar. Water has polar bonds and is a polar molecule. One way to have a molecule be polar is for there to be lone pairs on the central atom, which push the molecule into a geometry which causes the dipoles not to cancel out. Another way for a molecule to be polar is for the magnitudes of the dipoles to be different due to having different atoms around the central atom. For example, in the OCS molecule, the CO bond is more polar than the CS bond. Even though the molecule is linear in three-dimensional space, because the magnitudes of the polarities are different, the bonds do not cancel out, and there is an overall dipole pointing towards the oxygen. You can draw a sketch of each molecule in 3D and draw the vector arrows to figure out whether a molecule has a dipole or not. A quicker way is to memorize some polarity rules. These polarity rules are related to the concepts we just talked about with magnitudes and directions of the polarity vectors. Our first rule is that if all the terminal atoms are the same, and there are no lone pairs on the central atom, the molecule is always nonpolar. Having all the terminal atoms the same is related to the magnitudes of the vectors. The magnitudes would all be the same because the polarities would all be the same. Having no lone pairs is related to the directions of the vectors. Remember, lone pairs take up space and affect the geometries of molecules. They have their own polarity that would be different compared to the polarities of the bonds. If there are no lone pairs, there is nothing that will have a different polarity compared to the bonds, and the molecule can be nonpolar. If the terminal atoms are not all the same, the molecule is probably polar. You would need to draw the 3D picture with the vectors to be sure, because certain geometries could allow it to be nonpolar. But for the purposes of this class, if you see that the terminal atoms are not all the same, it will be polar. If there are lone pairs on the central atom, the molecule is probably polar. If you want, you can memorize that the bent, trigonal pyramidal, seesaw, T-shaped, and square pyramidal geometries are always polar. Personally, I think it's easier to memorize the two exceptions, square planar and linear. These molecular geometries allow a molecule to be nonpolar as long as all the terminal atoms are the same, even though there are lone pairs on the central atom. Try drawing out one of these molecules with the polarity vectors and see if you can understand why. Essentially, the lone pairs will cancel each other out in three-dimensional space, and the atoms will cancel each other out in three-dimensional space. Be careful in assuming lone pairs will cancel each other out, though. It is only with these two particular geometries. For example, even though we often draw the Lewis structure of water with the lone pairs across from each other, in the three-dimensional model, we can see that they are actually at an angle to each other and would not cancel each other out in three-dimensional space. Identify the nonpolar molecules in the following group: HBr, CH4, CHCl3, CCl4. Is it A, HBr, B, CHCl3 and HBr, C, CCl4, or D, CH4 and CCl4? The correct answer is D, CH4 and CCl4. Both of those molecules have no lone pairs on the central carbon atom, and all four atoms around the carbon are the same element as each other, so they are both nonpolar. HBr is polar because all it has is a polar bond. It does not have any other bonds that could cancel it out to make the molecule nonpolar overall. CHCl3 is polar because the terminal atoms are not all the same. In Chemistry 152, you will learn how to use polarities to predict which intermolecular forces a molecule has. For now, you should be aware that there are some properties determined by the polarity of the molecule. One thing that happens with polar molecules is that because they have a partial positive side and a partial negative side, they can align with an electric field. Another property is that like dissolves like. Polar substances are able to dissolve other polar substances. Nonpolar substances are able to dissolve other nonpolar substances. However, polar and nonpolar do not mix well. In summary, you should be able to draw the Lewis structure of a molecule and count the number of domains. From the number of domains, you can determine the electron domain geometry and approximate bond angle. You can count the lone pairs on the central atom in your Lewis structure, and from the number of domains along with the number of lone pairs, you can determine the molecular geometry. You can also determine if the bond angle is exactly or less than the typical value. Finally, using the Lewis structure and the molecular geometry, you can determine polarity of the molecule.